What specific problem do insertion language models, ILMs, aim to address that neither autoregressive models, ARMs, nor masked diffusion models, MDMs, can solve effectively?
Insertion language models, ILMs, aim to address the limitations of both autoregressive models, ARMs, and masked diffusion models, MDMs, by enabling the insertion of tokens at arbitrary positions in a sequence while maintaining strong dependencies between tokens. Unlike ARMs, which generate sequences in a strict left-to-right order, and MDMs, which can violate token dependencies by unmasking multiple tokens simultaneously, ILMs predict and insert one token at a time in reverse order. This approach allows ILMs to handle complex reasoning and long-horizon planning tasks more effectively, as demonstrated in empirical evaluations, where ILMs consistently outperform ARMs and MDMs on tasks like generating paths on star graphs and solving zebra puzzles. Additionally, ILMs excel at arbitrary-length text infilling, a task where both ARMs and MDMs struggle due to their fixed constraints. Thus, ILMs provide greater flexibility and effectiveness in sequence generation compared to their predecessors.
How does the proposed method, insertion language models, ILMs, work? Please illustrate it step by step, including the training and inference processes.
Insertion language models, ILMs, operate by learning to insert tokens at arbitrary positions within a sequence, addressing limitations of both autoregressive models, ARMs, and masked diffusion models, MDMs. During training, the model receives a sequence with some tokens dropped, and it learns to predict the missing tokens one at a time, using a tailored denoising objective that approximates the distribution over possible denoising steps. The training process involves two main components: a token insertion component that predicts the probability of inserting a token between existing tokens, and a binary decision component that determines when to stop the generation process. In the inference phase, ILMs generate sequences by inserting one token at a time, predicting both the token and its position in the existing sequence, which allows for flexible generation without the constraints of fixed-length masks. This step-by-step insertion continues until the model decides the sequence is complete, enabling it to handle complex dependencies and variable-length sequences effectively.
Can you provide a simple yet illustrative example to walk through the inner workings of ILMs, highlighting how tokens are inserted and how dependencies are maintained?
Insertion language models, ILMs, operate by predicting and inserting tokens at arbitrary positions within a sequence, one at a time. For instance, consider the input sequence, the chef added to the dessert. If we drop the token sugar, the ILM would learn to predict sugar and decide where to insert it, potentially resulting in the chef added sugar to the dessert. This process maintains token dependencies because the model can consider the context of the existing tokens when determining the appropriate position for insertion. Unlike masked diffusion models, MDMs, which replace drop tokens with a mask and may violate sequential dependencies, ILMs directly remove tokens and generate them in a flexible order, allowing for coherent and contextually appropriate outputs. The model's training involves a denoising objective that approximates the distribution over possible sequences, ensuring that the generated tokens fit well within the existing structure of the sequence.
What are the practical advantages of using ILMs over ARMs and MDMs, particularly concerning sequence generation and constraint satisfaction tasks?
Insertion language models, ILMs, offer several practical advantages over autoregressive models, ARMs, and masked diffusion models, MDMs, in sequence generation and constraint satisfaction tasks. Firstly, ILMs can insert tokens at arbitrary positions in a sequence, allowing them to handle strong dependencies between tokens without being restricted to left-to-right generation, which is a limitation of ARMs. This flexibility enables ILMs to excel in tasks requiring complex reasoning, such as the zebra puzzles, where they achieved a sequence accuracy of 90%, outperforming both ARMs and MDMs. Additionally, ILMs demonstrate superior performance in generating variable-length sequences, consistently generating correct paths in planning tasks on star graphs, even when ARMs and MDMs struggle. Finally, ILMs are competitive with ARMs in unconditional text generation tasks, while significantly outperforming MDMs in arbitrary-length text infilling, showcasing their versatility and effectiveness in various applications.
How was the effectiveness of ILMs validated in the empirical evaluation? What datasets and metrics were used to compare their performance with ARMs and MDMs?
The effectiveness of Insertion Language Models, ILMs, was validated through empirical evaluations on various tasks, specifically using a synthetic planning task on star-shaped graphs and zebra puzzles, as well as unconditional text generation and infilling tasks. For the planning tasks, the models were assessed on their ability to generate correct paths in star graphs of varying complexity and to solve constraint satisfaction problems in zebra puzzles. The datasets used included the 1 billion word benchmark, LM1B, and tiny stories for text generation, where ILMs were compared against autoregressive models, ARMs, and masked diffusion models, MDMs. The primary metrics for comparison included sequence accuracy for planning tasks, negative log likelihood, NLL, for unconditional generation, and entropy for evaluating the quality of generated text. The results indicated that ILMs consistently outperformed ARMs and MDMs on planning tasks, and excelled in arbitrary-length text infilling, while being competitive with ARMs in unconditional text generation.
What specific results were achieved with ILMs in the context of the experiments conducted, particularly in relation to the synthetic planning tasks and unconditional text generation?
In the experiments conducted, Insertion Language Models, ILMs, demonstrated superior performance on synthetic planning tasks, specifically generating correct paths on star graphs, where they consistently outperformed both autoregressive models, ARMs, and masked diffusion models, MDMs, especially in scenarios with variable path lengths. For the zebra puzzles, ILMs achieved a sequence accuracy of 90%, surpassing both ARMs and MDMs, showcasing their effectiveness in constraint satisfaction tasks. In terms of unconditional text generation, ILMs performed slightly better than MDMs, and were competitive with ARMs when evaluated using generative perplexity metrics. Overall, ILMs excelled in arbitrary-length text infilling, outperforming MDMs, while maintaining comparable performance to ARMs in unconditional generation tasks. These results highlight ILM's ability to handle complex dependencies and generate coherent sequences effectively.